So this is E658, lecture 17. So in the last class, we basically saw some intuition why this model for a fully differential operational amplifier makes sense. And this is a model that you will all be using. So this is A by 2 times VIP minus VIM, and this is also A by 2 times VIP minus VI, and it is drawn in this fashion. And the differential gain is the ratio of the differential output voltage to the differential input voltage is simply A. Now, in practice, as I kept saying, there is finite speed associated with the op amp, and the derivation of the dynamics proceeds in a manner very similar to what we saw with respect to a single-ended op amp. You want more, you know that from a single stage you cannot get too much gain. So you cascade, right? You put another common source amplifier in cascade, and then you realize that when you close a loop of this nature, the quality factor of the closed loop system will be very, very high, okay? And the poles will be dangerously close to the j omega axis. So to fix this problem, what will you do? You put a dominant pole and make it look like a first order system, and this is all the same old that we have seen over and over again. In other words, a more realistic model would be that the output VOM will be A by 2 times Vx, and this will be another A by 2 times Vx, where Vx is nothing but this is R DOM, this is V. So this is VIP minus VI, this control source here. So the output voltage is not simply a constant gain times VIP minus VIM. So VOP minus VOM is seen to be VIP minus VIM. The differential output is the differential input times A times 1 by S R dominant C dominant, and this can be recognized as the 1 over the dominant pole. And this is very similar to the same form that you're used to from earlier classes, which is VIP minus VIM times A divided by 1 plus S by omega D. And A times omega D represents the gain bandwidth product of the operational amplifier, assumed to be a single pole system. For the purposes of this course, this model is adequate. When this becomes inadequate, I will introduce new artifacts in the model which hopefully account for things that one sees in a real op amp. As we discussed yesterday, the input of this op amp is going to be a differential pair. So the low frequency input impedance of the fully differential op amp is infinity for both common mode and differential mode signals. In practice, of course, there is going to be a small parasitic capacitance corresponding to the gate capacitance of the input transistors. There is going to be some output capacitance at VOP and VOM, and at any rate, the input current flowing in is 0 if the fully differential op amp is realized using MOS transistors. With bipolar transistors, of course, there will be base current, which makes them quite unsuitable for switch capacitor applications. So, any idea why the minus is put here and the plus is put there? Why couldn't I put minus plus and plus minus? So this is VIM, VIP, VOP, VOM. Why does it make sense to do this? We know that anyway we are going to use this in a negative feedback configuration. So, whatever we do, we will connect this back to through some feedback network to the negative terminal, right? If we had drawn this with minus minus and plus minus, then all these wires would keep crossing and confuse the hell out of us, right? So, it makes sense to draw this way. Okay. So, let's quickly look at a practical example of a fully differential design. We know that a single-ended design, for example, of a switch capacitor sample and hold is, this is Vi, this is phi 1, this is phi 1a, this is the sampling capacitor. Once we've held the input sampled on the sampling capacitor, it's not just enough if you hold it on the capacitor. This capacitor must be, you eventually want to quantize the voltage that is held on the capacitor. Whatever I use to quantize shouldn't load the capacitance and steal away all the charge on the capacitor. Then I will be quantizing something which is. So, one way of doing it was to put a voltage controlled voltage source, buffering the capacitor, making sure that charge on the capacitor is safe. Another way of doing it, using switch capacitor techniques, is the following. And the basic idea is that if I had an op amp and if I had a capacitor like this, there was a capacitor charged to a voltage of Vx. If I put this around an op amp like this, what do you think the output will be? It will be minus Vx. On the other hand, if to make the output plus Vx, all that I need to do is take the capacitor. If I took a capacitor charged to voltage Vx and put this around an op amp in this fashion, then the output voltage will be plus Vx. What is the output impedance of this composite beast? The output impedance is simply 0, because the moment you try and inject any current into this node, clearly the voltage will attempt to, if you push current into this node, this voltage will attempt to go up. If this node voltage goes up by some delta V, what do you think will happen to this node potential? Go up by how much? The same amount. Why? The charge on the capacitor is fixed, it can go nowhere. The input impedance of the op amp is infinite. So if this goes up by delta V, this also goes up by delta V. Thereby, there's a delta V difference between the two terminals of the op amp, which causes the op amp to administer a huge kick to this node, pulling this node back towards what it was earlier. So the output impedance intuitively is seen to be 0 with an ideal op amp. In a real op amp, of course, it will be low. And so that basically means that you can use this to go and drive you have figured out two things. One is you know how to sample the input onto a capacitor with reasonable amount of fidelity. For example, you would use a bootstrapped switch here, you would do bottom plate sampling, blah blah blah. Okay. The moment you have sampled stuff onto the capacitor, now you also know a way of making sure that whatever you do, the voltage on the capacitor is no longer corrupted and it in principle will be able to drive heavy loads that one might expect from a contraption that quantizes the output. So the next thing is to put these two things together in a single circuit. What will you do? During one phase, you will sample the input signal. It's now the input is safely sampled and held as charge on a capacitor. Okay. The next job is to take this capacitor and flip it around an op amp. So a logical thing to do would be the following, which is during phi 1, I do what so this is the so-called sample and this is the so-called hold. So combining both of them into one circuit, this is phi 1a, this is Vin, and what the voltage that's held on the capacitor is Vn at what time? At what instant is the input sampled? At the falling edge of phi 1a. So once the input is sampled, what should I do now? I have this op amp here. Which side should I connect to the negative input? Left plate or right plate? I want an output also of Vin eventually. So what should I do? The right plate should be connected to this guy. So what should happen to the left plate of the capacitor? So in phi 2 must be connected like this. And what should I do with the left plate? You understand? I mean, that's how it is with switch capacitor circuits. Switch capacitor circuits will look notoriously complicated when you look at them for the first time, because there will be this bazillion switches and op amp and capacitors. But when you look at it carefully, you will find that what is happening is indeed quite simple. So let's see if we can make any simplifications to this. Do we really need this switch phi 2? What should I? Should I make that an open circuit or a short circuit? Make it a short circuit. So when phi 1 is on, clearly this node potential will go to 0 because the switch is shorting it. Okay, and in any case, you're not really worried about the op amp out phase phi 1. You're only interested in the hold phase of the sample, and hold is simply which phase? If you plot the output of the op amp, how will it look? Let's say this was phi 1, this is phi 2, and we know that these are all should be non-overlapping. So this is phi 1, this is phi 2. So if I plot the output of the op amp, what do you think it will look like? During phi 1, what is the output voltage of the op amp? 0. Why? The negative terminal is shorted to ground. Correct? So the difference between the two input voltages is 0. So in principle, if the op amp is A times this voltage minus this voltage, the output should be 0. So what will happen? The output of the op amp will remain 0 here. When both phi 1 and phi 2 are, for example, when phi 1 is open, what happens? First phi 1 is high, then both the switches are open. Okay, this is the non-overlap period between the two of them. So what do you think will happen to the op amp? The output will continue, in principle, continue to remain the same. Then what will happen? Then phi 2 is turned on, so the op amp will go to Vin. Then what will happen next? During the non-overlap period, it is now not clear what will happen, right? But in practice, what will happen is that there will be parasitic capacitance at the input nodes of the op amp. So they will tend to hold, they will have the same voltage, okay, even when you turn off phi 2. So during this overlap period, depending on the parasitic capacitances, this would tend to behave like this. Then what happens? Phi 1 comes again, the output will go towards ground. So this period is the hold period. And faster the op amp. Can you make any comment on the behavior during the hold period? You would think that things would become faster at. So that brings up an important point. So is there negative feedback during the hold period? When will the op amp behave like a voltage controlled voltage source? Or when can you say that the two input terminals of the op amp are at the same potential? When there is DC negative feedback, okay. So in phi 2, is there DC negative feedback? So during phi 2, okay, this is being charged to some voltage Vn. So the question is there DC negative feedback during phi 2? Okay, how will you figure out if there is DC negative feedback? Fine, right? So we do what we are used to, which is we cut the loop somewhere, yank up one end of the loop, then we see what comes back. Okay, and if what comes back is in the opposite direction of what, direction in which we yank the loop up, then there is DC negative feedback. So let me cut open the loop here. So if I yank this voltage up by delta V, what happens to this voltage? What happens if I move one end of a capacitor up by delta V? Okay, the argument is the capacitor should retain charge. The reason why charge on the capacitor will remain on the capacitor is because the op-amp input impedance is infinite. So if I yank one end of the capacitor up, what happens? The other end also must go up by exactly the same amount, right? So this also goes up by delta V. If this goes up by delta V, what happens to the output of the op-amp? Goes down by minus A delta V. So is there negative feedback around the op-amp or is there no negative feedback around the op-amp? There is? Definitely. Are you convinced?
So, but is it yanking operation a step operation?
No, I can yank and keep holding it like that forever, right? The argument is that when I yank this output, I'm supposed to put DC. So maybe the fact that you're yanking things up very quickly, maybe that's what's making this work. Okay, but if that is true, if I yanked it up and held it for a long time, if there was no DC feedback, eventually the output of the op-amp should come down to 0. But clearly you see that if I could yank the right end of the capacitor up by delta V and hold that for any amount of time, and the output of the op-amp will not change at all, right? It will be minus A delta V. So there is definitely DC negative feedback. An easier way of convincing you would have been to make the common argument that if you don't draw any charge from a capacitor is charged to a voltage V is equivalent to a battery of voltage Vn. How many of you agree that there is DC negative feedback around the op-amp now? There's no disagreement at all, right? And all I've done is replace the battery with a capacitor charged to the same voltage. And based on the understanding that since I'm not going to be drawing any charge from the capacitor anyways, the two of them are exactly identical, so there should be no issue. So the question is, if there is DC negative feedback around, the question is, we accept that there is DC negative feedback around here, okay? Then a legitimate question is the following. So this we understand that there is DC negative feedback. What about this? Is there DC negative feedback around the op-amp in this circuit on the right? Okay. We'll do what we're used to. We'll cut the loop here and yank this guy up by delta V. Okay. So what happens to this voltage instantly? Instantaneously it jumps up by delta V. The moment this jumps up by delta V, what happens? Current flows to the resistor. If current flows to the resistor, it means that the charge on the plates is getting lost. So you will find that there is the output voltage here, which would immediately jump down, would eventually settle off to, it will come back to 0, okay, simply because when the capacitor is getting discharged to this resistor. So this is an example where there is AC negative feedback, but there is no DC negative feedback, and AC negative feedback is useless as long as you don't have this embedded in a larger negative feedback loop which forces the output of the op-amp to sit around in its high gain region. Yeah, but at T, when I say DC, it means that at T equal to infinity, if I come back and look tomorrow, I should still make sure that the op-amp output is in the opposite direction of what I've pulled up. So we know that there is no DC negative feedback here. Then the third question is, what about this? Let's say this capacitor is initially charged to 0. This capacitor is initially charged to some Vx. So is there DC negative feedback around the op amp? So if both these capacitors were identical, for example, there's nothing holy about both capacitors being identical, but that's good enough to illustrate the point. Again, there should be no need for guessing. When you're in doubt, start from first principles and go with it. So if I cut the loop here and yank this up by delta V, what happens to this voltage? Delta V by 2. Why delta V by 2? It's nothing but a capacitive divider, right? I've cut this guy up and I have two capacitors in series. If I yank one end of the capacitor chain by delta V, the guy in the middle will go up by delta V by 2. If this goes up by delta V by 2, what do you think will happen to this guy? Go down by minus A delta V by 2. So there is definitely DC negative feedback. However, the loop gain for DC now is 1/2 what it was when this input capacitor wasn't there. And this is very similar to the resistor situation. So there is DC negative feedback here also. So coming back to our sample and hold. During phi 2 clearly there is negative feedback. What about during phi 1? During phi 1 there is no negative feedback around the op amp. So the op amp is basically open loop. But that may not be too much of a problem simply because we are not worried about the output during phi 1 anyways. So and clearly, as I have indicated to you several times before, whenever I say ground in a single-ended op amp circuit, what does that actually mean? What does this ground actually mean? It means VDD by 2. Now, let's talk about, now we have learnt about differential operation and all the marvelous advantages that accrue with it. So, let us this is the single-ended version we just seen. Now, let's say we want to convert it into a differential input, differential output, sample and hold. This basic architecture is often called the flip around sample and hold, simply because the input capacitor is flipped around the op amp. Now, if I want to make it fully differential, what would I do? Let's talk about the sampling first. What would I do? If I have a differential input signal, what does it mean? I have two inputs, one which is VCM, let me call the common mode VCM, plus VI, which needs to be okay, so this is C, phi 2, this is C, this is phi 1 again, C, VCM minus VI. So what is the voltage stored on this capacitor at the once it's sampled? It's simply VI. Similarly, the voltage on this capacitor is minus VI. Then the next job is to take this and flip this around a fully differential op amp. This is phi 2, this is. Once phi 1A is falls down, the voltage on this capacitor C is VI, the voltage on the lower capacitor is minus VI. Then when I flip them over, what is the output voltage? In phi 2, the op amp will make sure that the output voltage is the difference between these two output terminals is some large number times the difference between these two voltages. And since there is DC negative feedback for the differential op amp in phi 2, it follows that the difference between these two terminal voltages in phi 2 must be what? In a single-ended op amp, these two terminal voltages will be the same if there is DC negative feedback. Okay? In a differential op amp, the difference between these two guys will be 0. So, what it means is that if these two voltages are the same, what do you think that voltage will be? We don't know. Let's call that some, no need to guess. Okay? So, let's call that VCMI. The only thing that the differential op amp is making sure is that the difference between the two inputs is 0. Nothing is known about the absolute value. We want to find what it is eventually, hopefully. So we call that VCMI. What is the voltage across this capacitor? VI. What is the voltage across this capacitor? VI. So, and we know that the output of the op amp will be the difference between the output voltages is A times the difference between the inputs, but the absolute output voltages will be what? VCMO plus some large number times the differential input, and VCMO minus a large number times the differential input. So, this voltage should be VCMO. What should the output voltage be on this leg? Plus VI. And what will this be? VCMO minus VI. So, what do you think what will VCMI be? Look here, during phi 2, this is what happens. So, this voltage is VI, this voltage is VI, okay. The difference between these two nodes is 0. So, the difference between these two nodes must be, that number happens to be 2 VI, okay. So, but we know that the op amp will force the output common mode because of the common mode feedback loop, whose details I went into yesterday, will force the output common mode to be VCMO, right. So, the difference between these two node voltages must be 2 VI and the common mode must be VCMO. So, it follows that this voltage must be VCMO plus VI and this voltage must be VCMO minus VI. Then the input, so now that basically means if this voltage is VCMO plus VI, right, and the drop across the capacitor is VI, then the voltage at this node must be VCMO. What about this voltage? Will also be VCMO. So, what do you see? During phi 1, the input common mode voltage of the op amp is, when phi 1 is high, what is the input common mode voltage of the op amp? It's VCM. During phi 2, what is it? It is VCMO. So, it basically means that the input common mode of the op amp is jumping up between phi 1 and phi 2. So, this is in many cases not desirable, not because it's a fundamental problem, but in many cases you're all aware that every op amp has got a so-called common mode input range. If the input common mode voltage becomes too low, then if you have an NMOS differential pair, the tail current will get pushed into the triode region. If the input common mode becomes too high, then you'll go and push the low transistors into triode. So, there's a very definite, well-defined range for the input common mode, and it's often not a good idea to keep switching the input common mode of the op amp up by large values. So, a good choice for this whole thing, a good design choice is to choose VCMO is equal to VCM, which also happens to be make the input common mode voltage equal to the op amp output common mode. It's not, as I said, it's strictly necessary, but this is a good choice, which avoids the jump in the common mode at the input of the op amp between every time you move from phi 1 to phi 2. So this, as I said, this is a practically useful sample and hold. One thing here is that there is no gain, right? So whatever input is there, the output is the same as the input, except that the impedance is very low, so that this can now drive other circuits. Can somebody comment on what current is being supplied by the op amp? No current. Why? The charge on the capacitor is not being destroyed, right? You're just holding on to that charge, and the op amp only supplies the current that needs to be driven into the load. So if for example, there was some load impedance here, then the current which goes into the load is nothing but 2 VI by ZL, and that is coming from where? That can't come from the capacitor, simply because the capacitor voltage has to be fixed, because the input impedance of the op amp is infinite. All this current must be supplied by the op amp. Okay, that sounds like a fair thing, right? And the capacitor's job is to simply hold on to the input charge. It shouldn't have to supply current to the load. So in the next assignment, you will actually design a full flip around sample and hold. So you'll use the same bootstrap switch that you've done before, and this time I'll ask you to actually design the clock generator to generate the non-overlapping phases. So concluding remarks, one issue that somebody raised was, why don't I simply short these two Why bother about an input common mode voltage at all? Tell you what the question is. The question is, why not do this? So, is there any comments on this one? What is this potential now? Absolute potential. The answer given is, when phi 1a is on, the voltage, this all becomes one node. The voltage at this node is VCM. Is that correct? What about the initial charge on the capacitor? Is it known? The initial charge on the capacitor is not known, no? So, whenever you come across a situation where you cannot find the absolute potential at any node, right, you know that there is a problem of this nature. The absolute potential at this node cannot be figured out. That is the problem with this, which is why you need a voltage source there. The last question is, why bother about, earlier we used switch capacitor techniques to get gain. Why not put a gain and then use for example, this is an example of a fully differential amplifier. This is R1, this is R2. The differential gain is minus R2 by R1. This is just a fully differential analog of minus R2 by R1 circuit that you know. The question is, why don't you do this and put your flip around sample and hold, for example, here? VCM and so any comments on why? But if you try to, if you have to compare apples to apples. So if you try to, okay. So a couple of issues. One, of course, is that this op amp now has to drive a switching load, right? And you anyway need an op amp to buffer to make sure that the voltage on this capacitor is not lost because charge is being sucked out. Okay, so you anyway need a low output impedance stage following this. So you might as well combine all of them into one circuit. And it turns out that designing op amps with high gain is easier when you're driving only capacitive loads rather than you're driving resistive loads like this. Okay, so these are the reasons why it makes sense to combine the gain and the whole operation into one op amp. Okay, all right. So I'll